And this is a continuation of the kinematics equation. So I believe you took a quiz on Friday, homework validation quiz, and then, so this is really a continuation of kinematics. So this really isn't a new unit, this is just an extension of it. And everything we've been doing is in one dimensional, which means kind of in a straight line kind of fashion. Like the problems we did last week, a car accelerating from 25 meters per second to 35 meters per second really have been just on this line. Nothing at any sort of angles or going in both the X and the Y. This is free fall, which is going to be obviously something like, I've got the wiffle ball here, I drop it, this is free fall, straight up, okay? And so this is gonna be on a linear line just along the Y axis or straight up and down. All right, so if this is free fall, this is an object that when I let go is under what? Under what concept? What's causing it to go downward? Gravity, right. Now is it causing it to go downward? It's accelerating downward. All right, so we're gonna be talking about what the gravity influence in there as well. When I talk about free fall, it's going to be doing these three things. One is from releasing from rest and going straight down, or you give an initial velocity going straight down. So when I release it, okay, it's not at rest, so it's going to be going straight down at an initial velocity. And the acceleration of gravity will still cause it to speed up again. All right. And then the third scenario is going straight up, which means when it goes straight up, it's going to eventually do what? Stop and then turn around and come back down. Okay. And those are the three scenarios wrapped up in free fall that you'll kind of have to recognize as well. So there's going to be buried givens in this. And one of the buried givens I talked about last week when I talked about kinematic equations is if it says something's in free fall or you're dropping something on Earth, the buried given is the acceleration of gravity is negative 9.8 meters per second squared. That is the acceleration rate for gravity of any object on Earth, whatever mass, how heavy or light, it's going to accelerate at that rate. Okay, without air resistance. I'll talk about that in a bit. All right, so that will be a buried given on some things. What will be another buried given if I'm dropping it from rest, dropping it off a cliff, dropping from a bridge, blah blah blah? What's another buried given? Yeah, initial velocity is going to equal what? Zero, right. That's so depending on what the problem reads, drop from rest, drop from a bridge, whatever, it's going to have an initial velocity of zero, all right? Conversely, you can have another one where if something is tossed upward at initial velocity of 10 meters per second and it asks how high did it go, well then what's another buried given up there? A final velocity would equal what? Zero, as long as it's referencing how high did it go, what was it at its peak, as long as it's referencing that peak. Okay, so there's going to be buried givens in each of those varied scenarios. All right, so any questions so far on what some of these buried givens will be? And again, as I said, free-falling object which is falling under the sole influence of gravity. Free-falling objects do not encounter air resistance. We're going to assume there's no air resistance in all of our problems, all right? Physics is tossed based on the universe. We're just lucky to have air. Really, the core parts of physics are really kind of calculated in absence of air resistance. Now, air resistance is part of fluid dynamics. That's a different kind of physics itself. All free-falling objects on Earth accelerate downwards at a rate of 9.8 meters per second squared if we're on Earth. If I put you on Mars, is this still valid? No, it's now you're going to have to use the acceleration rate of Mars. Sometimes it'll be given to you, you might have to look it up. Mars is negative 3.6 meters per second squared. On the Moon, it's going to be something different, negative 1.6 meters per second squared, or negative 1.67 meters per second squared, et cetera, all right? The equations important to free fall. The equations don't change. The other two that are with this are also still in play. Doesn't mean they're not in play. These two are a couple of key examples of how they might change a little bit. I always borderline where I want to keep this slide in there as well. If it's dropped from rest, what's going to wind up happening is if the initial velocity is zero, that component goes bye-bye, doesn't it? Because 0 times anything is 0. That whole thing drops off. And what you're left with is just 1/2 AT squared. All right, so we see that. Also, initial velocity equals 0. In this case, that's all going to drop off, and what you're left with is this equation. And you can memorize these if you want to. If it's really just me, I mean, if you want to memorize those, you can. I would highly recommend just sticking with the ones you know. Plug in the 0, let it get taken out. and let it calculate on its merry way. All right, that way you don't make any sort of errors. All right, but you're more than welcome to say, well, if I know it's dropping from rest, I can use this version of it and not even put that in there. I'm fine with it, as long as you are applying it in the right scenario. You have to be careful with that. All right, any questions on this? Clearly there's changes in velocity, changes in displacement, just like we talked with when we had the acceleration unit. As time goes along, the velocities are going to increase. After all, that's what the definition of acceleration is. 9.8 meters per second squared per second of movement. Okay, so after 1 second, it'll be going 9.8 meters per second towards the origin. And after every second goes by, you're going to add 9.8 to the previous one. After all, that's the definition of acceleration. I mean, after 2 seconds, it's going to be negative 19.6 meters per second squared, or 19.6 meters per second towards the origin or towards the Earth. And it's going to get faster and faster as it drops. All right. And the same thing with displacement. If it's at constant velocity, the displacements were even. Under acceleration, the displacements are going to get further and further apart as you go further in time. Those displacements compared to each other are going to get further and further. After all, per unit of time, that gap's going to increase, right? Which everybody, I believe, can kind of see. That's just a straight up kind of a regurgitation of what we talked about in the acceleration unit, all right? So representing free fall graphically, all right? You're not going to need to really know this. We already went through the graphs, but it's starting away from the origin, and it's going to be falling towards the origin. So your position versus time graph is going to have a negative slope, and if it's going faster, it's going to be shallow to steep. So it's going to be that. And then, of course, if it's going towards the origin, the velocity will be in the negative quadrant. Okay, that's a no-brainer. I'm not going to throw this at you again. Probably not, but it's good to know. All right. Do heavier objects fall faster? Do heavier objects fall faster? Yeah. Yes, no? Okay, you say yes, you say no, right? So if I take this wiffle ball and this stool and I drop them, will they hit at the same time? No. Okay. Without air resistance, will they? Yeah. They will. Yes. Now in air resistance, I bet you these will still hit at the same time. This would be kind of fun to drop this, wouldn't it? Should I drop it? Yeah. No, I better not. It could be too much noise for Coach Cooper or Coach Jones. No, the heavier objects do not fall faster. All right. Yes, I can put this remote in a feather, and I drop it. The remote is clearly going to hit first, and the feather will kind of do this. But it's not because gravity is different for the feather. It's because we're in air, and it's encompassing air resistance. All right, one of the coolest lab experiments ever done was on an Apollo mission back in the late 70s, early 70s, maybe in the late 60s. They took a hammer and feather to the moon. They literally sent it to the moon with them. And then when they went out on the moon's surface, one of the astronauts dropped a hammer and they dropped a feather at the same time on the moon. After all, what a perfect scenario, because the moon does not have a what? Atmosphere, right. So it doesn't have any air for air resistance to even factor. So what they did, and I'll probably find this and I'll show it to you tomorrow. What they did is they dropped it, and certainly enough, the feather and the hammer hit at the exact same time. Because gravity is the same. Doesn't matter the mass, gravity acts the same per object. All right. So no, heavier objects do not fall faster because of that. Don't worry about motion maps, but it's a good description. Again, kind of reiterating what we talked about in the previous slide. The velocity is going to get greater as time goes along, but the acceleration is constant. The acceleration does not change. All right. Now, the problem-solving strategies, there's your buried given. If you're on Earth, use negative 9.8 meters per second squared. When completing free fall problems with the displacement height, the final velocity must be negative. Again, if you're going towards the Earth, your velocities are going to be negative. If you're going away from the Earth, your velocities are going to be positive, or all your signages are going to fall under the same signage requirement as we've talked about before, because these are vector components, so the signage matters. And you'll see this in a second on some of the problems. Also the buried givens. Note that if it's from dropping from rest, an initial velocity is equal to 0. If it's at the top, the final velocity could equal 0, depending on what the problem says. So the same problem solving strategies we talked about before and some of the kinematics equations apply here to free fall. All right. Any questions on this? Pretty straightforward. All right. Now, this obviously it includes objects on the way up, also objects on the way down. Velocity decreases on the way up, velocity is 0 at a maximum height, acceleration is still negative 9.8 meters per second squared the entire trip. So again, just a reiteration of some of the buried givens on some of this. All right, so that's it on the premise of freefall. All this is an extension of kinematics. So here's 3 example problems that we are going to go through. This is on your last 3 pages. You will follow along and will calculate as I go along. These are not shown as actual work. So we're going to do our same procedure on this, our same solving procedures. The first thing we're going to do is what? List the givens, right? Okay, so let's list these givens. A stone is dropped from the top of a cliff. It is seen to hit the ground below after 3.5 seconds. How high is the cliff? So what is this asking you to solve? Yeah, it's asking to solve for displacement, isn't it? Okay, and then let's list everything that we have given here. I see after 3.50 seconds, I have time equals 3.50 seconds. Cool, is that all we have? Yeah, now we're on Earth, so we also know that acceleration equals negative 9.8 meters per second squared. Cool, what's another given, or is that it? Yeah, our initial velocity is 0. A stone is dropped from the top of a cliff. If I was to kind of draw this, there's a cliff, a stone is dropped from rest, it's going to get further. Once it reaches the ground, it's going to hit the ground, so it is going downward. So we also have an initial velocity is going to equal 0 meters per second. All right. Before I calculate this out, what should my displacement calculate out to, a positive or a negative? It's going to have to calculate out to a negative. We know for sure. Why? This is being displaced downward. It's not being displaced upward. If it's being displaced downward towards the origin, which is Earth, it's going to have to calculate out as negative. So if it calculates as positive, you've done something wrong. All right? So then we have to ask ourselves, which equation has displacement, time, acceleration, initial velocity, and it's going to be this one. And of course, I'll put displacement, I'll put the X in red. Displacement equals initial velocity times time plus 1/2 AT squared. Then remember, that's the second step. Find the equation to use given the givens that you have. All right, well now we plug everything in. This is going to be displacement is going to equal, my initial velocity is 0 times 3.5 plus 1/2 times negative 9.8 times 3.5 squared. All right, cool. That takes itself out because 0 times anything is 0, and we're kind of left with this component right in here. And this isn't algebra. This is straight up solving. The variable is already by itself, so all we have to do is PEMDAS and run this whole thing through. So we're going to put displacement is going to equal, I'm going to say half of negative 9.8 is negative 4.9. And then 3.5 squared, my calculator's over here, 3.5 squared, 12.25, so 4.9 times, negative 4.9 times 12.5, we can run that through the calculator, I think it's 60 point something, yeah. It's going to be displacement, it's going to equal 60.03, if I go to 2 decimal spots, negative 60.03 meters. And again, a negative times a positive is going to get you a negative number here, so it does calculate out correctly. All right. Everybody see what I did here? There's nothing new to this. This is the same thing you've been doing with kinematic equations, just applying the physics and the physical concepts of basically free fall. All right. Any questions on this one? Next one. A stone is dropped from the top of a cliff. It is seen to hit the ground below after 3.50 seconds. How high is the cliff? A stone is dropped. Oh wait, that's the one I just did. Sorry. Sorry, a foul ball is hit straight up into the air with a speed of 25 meters per second. A, how high does it go? And B, what is the velocity after 2.57 seconds? So we're again going to list our givens in this. How high it goes is what again? Displacement, isn't it? How high does it go? We're going to put x equals question mark. It says up in the air with a speed of 25 meters per second. We're going to call that my initial velocity equals 25 meters per second. Is that right, or should it be negative? It's positive, so that's right. Okay. We still have acceleration equal to negative 9.8 meters per second squared. Straight up in the air. How high does it go? Is there any other givens on this? Yeah, my final velocity is 0. In this case, it's 0 because how high does it go? Which means this thing's going to go up, so it's going to go up, and how high it goes, which means it's going to, at the height, it's going to have no velocity, is it? All right. So that does become a given here. So we ask yourself, what equation has final velocity and then displacement, initial velocity, acceleration? I could go to my kinematics equation and realize that final velocity squared equals initial velocity squared plus 2 times acceleration times displacement. All right. As a matter of fact, I'll do this here. I'll put my variable I'm solving for here in red, which is again displacement. All right, now I'm going to plug my variables in here. This is going to be 0 squared equals 25 squared plus 2 times negative 9.8 times x. All right, and then I start simplifying or whatever. This is going to be 0 squared is 0. 25 squared is 625 plus 2 times negative 9.8 is negative plus negative 19.6 times x. I mean, a plus and a negative here will change that to be negative. So I'm going to simplify this down to 0 equals 625 minus 19.6 times x. Okay. This one you got to go with algebra because the variable is not by itself. So what is my first move here? Deal with the 625 or the negative 19.6? Yeah, the 625, because we're doing SAD map here. So the negative 19.6 is being multiplied into the x with 625 being added to it. So we have to deal with addition subtraction first. We're going to subtract 625 because the opposite of positive 625 is negative 625. That'll cancel that out. 0 minus 625 is negative 625 equals negative 19.6 times x. Okay. Is there any more addition, subtraction? No, there's not. So what's my next and last move here? We're going to divide by negative 19.6. Because what's the opposite of multiplication? Division. Cancel, cancel. Before this was to even being calculated, was this displacement going to have to be positive or negative? Positive. Yeah, because this displacement asking how high it went. How high it went is away from the origin, so that displacement in this case has to calculate out as positive. And a negative divided by negative is going to give you a positive anyway. 625 divided by 19.6, which is 31.82. This is 31.82 meters, and that's positive. That's going to be my displacement. And there's my answer. All right. Everybody see what we did there? That's an classic algebra 1. All right. What is the velocity after 2.7 seconds? Well, some of these problems, it can be, well, sometimes the answer we get for the previous one we can use in the next one, but can we use this answer down here? Probably not, because it's saying, well, what's the velocity after 2.7 seconds? We don't know where that thing places it. All right, so really this whole thing resets, but what stays the same is initial velocity equals 25 meters per second. That does still stay the same. Acceleration of gravity is still negative 9.8 meters per second squared. And this time it says the time is equal to 2.7 seconds. It is asking to solve for what is the final velocity equals question mark. All right, then we ask ourselves, which equation has initial velocity, final velocity, acceleration, and time? We note that final velocity equals initial velocity plus acceleration times time, right, with the velocity we're solving for here. So final velocity is that we plug in, it's going to be my initial velocity, which is 25, plus my acceleration, which is negative 9.8, and time is 2.7. Right, this is straight up solving, no algebra here. I do have to do this right here, multiplication first. And negative 9.8 times 2.7, I believe is negative 26. And negative 26.46. So this is equal to 25 plus negative 26.46 plus a negative is the same as 25 minus 26.46, or you can straight up add that if you need to. And what is 25 minus 26.46? Says it's negative 1.46 meters per second. Is that even possible? That thing was getting tossed up. So why is my signage negative? Yeah, this tells us that after 2.7 seconds, it has already gone up past the peak, hasn't it? And is now on its way down. Let's repeat it with these calculations. It will factor that in for you. So this thing's already hit its peak, then at 2.7 seconds, it's just starting on its way down. Okay, it's just past its peak. So this is moving back towards the origin, right? Any questions on this? All right. The third example, all right? This one's kind of odd. I should have meant to kind of swap these. The last one, yeah. A ball is thrown, so the first example dropped from rest, second example tossed up. This one is being thrown vertically downward. A ball is thrown vertically downward with a velocity of 15 meters per second from the roof of a building that is 22 meters high. A, how long does it take to hit the ground below? This should say B. How fast was it going when it hit the ground? I'm going to solve this two ways, okay? Both ways will probably take a little bit of time. When I do it this way, it's going to probably be easier to solve for the B part first and then use B to plug it back into A. That's kind of the intention of this. But if I was to start from A ball thrown vertically downward with velocity says how long does it take for the ground below? Time equals question mark, isn't it? All right. Then I start dealing with my givens here. I'm going to put initial velocity equals 15 meters per second. Is that right? Correct. It needs to be negative 15 seconds because we threw this downward, and down is towards the origin. Down is negative in this case. The acceleration to gravity is still negative 9.8 meters per second squared. All right. And I've also got displacement equals 22. Is that right or is that wrong? Is positive 22 correct here? No, it's not, is it? What must this be? It has to be negative 22 because that's being displaced downward. The signage is going to be hugely matter here. All right. Now, we need to use an equation with displacement, time, initial velocity, acceleration. And it's going to be this one. Displacement equals initial velocity times time plus 1/2 a, okay, t squared. Now, in this scenario here, if I was to plug these in, before I plug them in, what's the dilemma we've kind of walked ourselves into here? It's quadratic, isn't it? Now, it looks like, okay, I've got this, and I'm down to t's, and we can solve, and you can, which I'll get to in a second. The problem with solving standard algebraically here is it's quadratic, or you're not going to be able to solve by standard 1, 2, or 3-step equations here. All right, and so that's what's going to make this a little bit of a dilemma. So then you start to ask yourself two things. I'll deal with the quadratic example in a second. However, can we go off the board here and go down a different kinematics equation to solve for something else to then use to solve for time? And I can look at the other equations that have time in it. The VF squared equals VI squared plus 2AX does not have time in it, so you can't use that, can you? But I'm going to use this space up here. We do have final velocity equals initial velocity plus acceleration times time, don't we? In other words, we can we can try to use time on this if we had final velocity, right? If you have final velocity, you can then solve for time here. So ultimately, an end game in this is try to get to this equation. And now, instead of solving for time, we're going to look for ways to see if we can solve for final velocity. May not be the case all the time, but we're going to try to solve for final velocity, given that we have displacement and given that we have VI and we have acceleration. And what you can then realize is that, well, I can use VF squared equals VI squared plus 2AX, and I'll be able to solve for final velocity and then use that to solve for time. And that's the route we're going to go. So final velocity, let's put that here, final velocity squared, let's see if that's visible. Final velocity squared is going to equal initial velocity, which is going to be negative 15 squared plus 2 times negative 9.8 times, I ran out of room here, times negative 22. All right, let's rewrite that. Sorry. Final velocity squared equals, that's going to be negative 15 squared plus 2 times negative 9.8 times negative 22. We're going to use that to solve for final velocity, all right? Which, ironically, when I solve for this, won't it give me that part? It'll give me part B, won't it? All right? So that's kind of the irony in this kind of question. So this is a straight up solve. So this is negative 15 squared. So I'm going to do 15 squared, because negative times negative is positive anyway. So this is 225 plus, and then 2 times negative 9 times negative 22, and negative times negative makes this positive. So that whole thing will stay positive. So I'm going to multiply all that together. And you get 431.2. And I add those together. And I get 656.2. 656.2. And that's going to give me my VF squared. Is that my final answer? Well, no, I got to take the square root, right? Square root of both sides. That will get me my final velocity will equal, and the square root of 656 times 2 is 656.2 is 25.62. So 25.62 meters per second, which is what it was going, the velocity it was going to be when it hit the ground. So what we've done is we've already solved for this one, haven't we? All right, we've already solved for that one. However, we still need the time up here. So remember, we're now going to take this and bring it all the way back up into here. All right, and we're going to note that final velocity is 25.
Coach Lambert?
Yeah.
Did you send Kate and Alan to the office to leave?
Yes.
Thank you.
25.62 equals my initial velocity of negative 15. By the way, what's wrong with this answer? Yeah, and it should be what? It has to be negative. Now, when we take this, when you take the square root of anything, what's the square root of 4?
2.
Or Yeah, it's gonna be 2 or negative 2, isn't it? A square root will give you 2. So when we did this, we had to look at both answers and say, for physics-wise, both answers are correct. But for physics-wise, which one is technically the correct answer? The negative, because this thing is doing what? Going towards the origin or away from the origin? Towards the origin. So negative 25.62 meters per second. All right. So this one must be negative 25.65 minus 15 plus negative 9.8 times, and then here we go, we're solving for time. This is the time we had up here, and I just run the algebra on this. I will wind up adding 15 to both sides, so I'm going to add 15 to both sides. Cancel, cancel. And this becomes negative 10.65 equals negative 9.8. And we know with time, it better always calculate out as positive because we cannot have negative time. We are going to divide both sides by negative 9.8. And negative 10.65 divided by negative 9.8 means time is going to equal 1.08 seconds. Does everybody see that? Okay. Yes, every once in a while, depending on the problem, and all these problems, they're very unique, you might have to go through a second equation to help you solve for the original one, depending on what is given in the problem. All right, does that make sense? Now, I'm going to do this the quadratic way. All right, so you could have foregone, if it's a quadratic, can I erase all this? Is everybody still doing this? Okay, if you wanted to forego and not do any of this, all right, you would then go down the route of quadratics. And so what I'm going to completely do, leave as much of this up as I can. All right. I do want to leave this up, so I normally would have just erased it. If I was to go back on this, and we had reset this whole thing. So there's where we originally were at, wasn't it? All right, and then when we plug this in, we would have had, so let's plug this in. This was negative 22 equals my initial velocity, which is negative 15 times time plus 1/2 times negative 9.8, and then this was t squared. Okay, and I can then clean this up further into this is negative 22 equals negative 15t minus 4.9t squared. I would realize this is quadratic. And if I'm going to need to run the quadratic equation, what must I make this equal to? 0, which means I've got to get this out of here by adding 22 to both sides. I'm going to square this up by declining exponents and rewrite it so it's easier to see to do the quadratic equation. This thing is now, I'll do this down here, negative 4.9 t squared minus 15t plus 22 equals 0. And I run the quadratic equation, which I'll put up here is negative b plus or minus the square root of b squared minus 4ac all over what? 2a, right? Is everybody familiar with that? How many of you have never done the quadratic equation before? Okay, that's good. That should be all of you. It's not quite true for first. So this is gonna solve for my time is equal to that. And what's happening in the quadratic equation is, as you know, the coefficient here is your a, the coefficient here is your b, and the constant here is the c, and you plug that thing right on in. Now, for those of you who don't do this, I would highly recommend that you put that b in parentheses. It's not necessarily stated in the equation. Why do you think I do that? Because I'm going to immediately drop. The biggest mistake people make is they see this as negative 15, because this is going to be your b, and they start this off as negative 15. And the equation will obliterate on itself right from there. Why? Because it's negative 15, which ultimately is going to make this what? Positive. And that's why I put parentheses there and say drop it in and let the signage do its work. All right. So what this really is, and I'll start working this down here, is we're going to do negative of negative 15 plus or minus the square root of negative 15 squared minus 4 times negative 4.9 times 22, right? All over 2 times negative 4.9. Then I'm going to step back and look and make sure I have this all set up correctly. The quadratic equation is amazing, but the problem with the quadratic equation is if you're not precise with it, it will spit out the wrong answer and you will never know unless something's completely jacked up. The quadratic equation will usually, but not all the time, give you how many answers? 2. Okay? There are cases where it will give you 1. There are cases it will give you 0. All right? Those will be handled accordingly. Now we just let the math run. And by the way, this will give me my time. Time equals that. Negative and negative 15 is positive 15. And this runs twice, doesn't it? You have to run this with the plus and then run this with the minus. So I'm going to run it 2 times. 15 plus, and then negative 15 squared plus the square root. 15 squared. 225. So this is 225 minus 4. This is a negative 4 and a negative makes this wind up being positive. Minus this changes to positive because minus 4 times negative 4.9 is positive, right? And so 4 times 4.9 times 22 is 431.2 plus 431.2. all over 2 times negative 4.9 is negative 9.8. This is also 15 minus the square root of 225 plus 431.2, all over negative 9.8, right? I'm going to run this 2, that's going to be, these 2 added together get you 656.2, and oddly enough, you're seeing the same numbers we worked in the previous part, didn't you? And so this is going to be 15 plus, and then this is 656.2. I'm going to take the square root of that, and that's 25.62, which is the velocity, plus 25.62 all over negative 9.8, and then this is going to be 15 minus 25.62 all over negative 9.8. If I was to clean this up, this is going to be 40.62 divided by negative 9.8, which equals 40.62 divided by negative 9.8 is 4.14, negative 4.14 seconds. And this is going to be negative 10.62 divided by negative 9.8. And does this look familiar? We just did that, didn't we? Okay? Which equals positive 1.08 seconds. Which one is right? Well, we already know that the answer is 1.08, isn't it? We know that this is correct, and this cannot be the answer because you cannot have negative time. So this is a case where in mathematics, you have two answers. In physics, you only have one, right? So you have two ways of solving that one. One by way of using two equations and then doing a multiple set, or you can go straight to quadratics and solve it. Either way works, all right? So there you go. That is free fall. Any questions? Any questions?
When you put the negative 15 squared, you have to put, when you square it, you have to put it in parentheses, right? Because otherwise you'll get a negative answer.
You have to, yeah, you just careful how you handle the sign. If anything negative, this will always be positive.
Right.
Whether it's negative soda, but you always want to make sure. Yep. If you want to do that, that's fine. All right. Cool. Have a good day.